Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over problem 3 of the 2003 AP Calculus AB release questions focusing on the flow rate function. All right, so let's take a look at a question. It reads, the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable and strictly increasing function r of time t. The graph of r and the table of the selected values of r of t for the time interval 0 less than or equal to t less than or equal to 90 minutes are shown above. So we have the graph and the table. Question part A. Use data from the table to find an approximation of r prime of 45. Show the computations that lead to your answer and indicate the units of measure. Okay, so don't forget to include units of measure in your final result because that's part of the answer too, okay? All right, so let's go ahead and start by taking a look at the formula that's going to guide our problem solving process. So let's take a look at the formula. So let's say we have a continuous and differentiable function f, okay? So let f be continuous and differentiable on an interval AB, okay? If, let's say there exists some C in this interval AB, then we can write down the following formula. Then F prime, the instantaneous rate of change of C, of the function at C, F prime of C can be approximated using the average rate of change. Average rate of change of the function on the interval AB. All right. So this basically applies to scenarios where you have a continuous and differentiable function and you want to estimate what the instantaneous rate of change is. The smaller the interval, the more accurate your estimation is. Okay. So what is the average rate of change of the function on AB? So f prime of C basically can be approximated using the average rate of change of the function on AB, also known as the slope of the secant line. So f of B minus f of A divided by B minus A. Okay, so this is approximating, we can call this, I like to call this IROC, approximating IROC using AROC. That's what we're going to be doing here. Okay, all right, so let's take a look at the function. We're going to be looking at the function r of t. So let's go to the table. So what we're doing is we are approximating the instantaneous rate of change at 45. So what you want to do is you want to look for the interval that contains t equals 45. Okay, so if you look at this collection of t values here, 45 falls in between 40 and 50. Okay, so you pick the interval that contains that value. The smaller the interval, the more accurate your estimation. Okay, so what we're going to do is write down the following remarks. So 45 is going to be our C, okay, and it's in the interval 40 to 50. Okay, so just as we had C in AB, so we can think about this as your C right here, and then this is the interval AB. So our instantaneous rate of change, the IROC at 45, is approximately the average rate of change of the function r over the interval containing 45, which is 40 to 50. Okay, and then using this formula right here, the average rate of change is basically r of 50. This is f of b minus r of 40, f of a, divided by b minus a, which is 50 minus 40. Okay. Now, if you take a look at a table, you evaluate the function at these two points in time. You end up with 55 minus 40, divided by 50 minus 40, which is 10. Okay, so we did our 50, 55, our 40, 40. Okay, so what we asked to include the units too. Okay, so the units of R of t is gallons per minute, and the units of time is in minutes. Okay, so what are we doing here? The numerator has the unit of gallons per minute, that's R, and then the denominator has a unit of time. So what we're looking at is gallons per minute for the numerator, divided by the unit of time, 50 and 40. See right here, 50 and 40, these are times. That's a minute, okay? All right, so if we want to simplify this, you can now go ahead and reduce. 55 minus 40 is 15 over 10. So gallons per minute, you can write this minute over 1. So you're going to have gallons per minute, and then you multiply the numerator by the reciprocal of the denominator unit, 1 over minute. All right, and that simplifies into 15 over 10. Just move the decimal point 1 point to the left there, and then you have 1.5, or you can reduce this to 3 over 2 is the same thing. Gallons for the numerator, minutes times minutes is minutes square. Okay, so R, the instantaneous rate of change at t equals 45, can be approximated by 1.5 gallons per minute square. And don't forget to box your final answer so your grader can easily identify where your solution is. All right, so let's go over how this is graded real quick. You get 1 point for using the difference quotient formula, just by using this formula right here to set up, and then get another 1 point by writing 1.5 gallons per minute square, for a total of 2 points for question number 3A. Oh, sorry, quick correction. You get 1 point for this portion, actually. You get 1 point for applying the table to the formula. Okay, and then you get your final point over here. All right, so let's look at the B part. It says the rate of fuel consumption is increasing fastest at time t equals 45 minutes. What is the value of R double prime of 45? Explain your reasoning. All right, so how can we convert this statement? The rate of fuel consumption is increasing at a particular time. How can we convert that into symbolic form? So one thing you want to note is that the rate at which the rate of fuel consumption is it could be the rate at which is changing. Okay, now when we're talking about changing, we're talking about the rate at which it is increasing, decreasing, or staying constant. Okay, the rate at which the rate of fuel consumption is changing is basically is the derivative of the rate of fuel consumption. Okay, so think about the rate at which the fuel consumption is changing at a particular time is basically the rate of fuel consumption, and that can be written as R prime of t. Remember, R is already a rate. We're looking for the rate of a rate, so we're taking the derivative of a function that's actually the derivative of another function. Okay, now R prime of t is basically the function that we're looking at here. So when R prime of t is if the rate of the fuel consumption is increasing fastest at this particular time, that means that R prime of t has hit its maximum value. Okay, so let's go ahead and write that down. If the rate of fuel consumption, is increasing fastest, then that basically means the rate of fuel consumption is, the rate at which the fuel consumption is increasing is basically the derivative r prime of t is at its maximum, is at its maximum. Okay? Now, if r prime of t is at its maximum, then we have a critical value there. Okay? So if r prime of t, actually, if the rate of fuel consumption is increasing fastest, okay, so if r prime of t, let's say t is 45, okay, because that's a particular time that we're looking at. If r prime of t, r prime of 45 is at its maximum, then there is a critical point there, is a critical point. Okay, so either we have a horizontal tangent, or we have no tangent at all, or we have a vertical tangent. Okay, so what kind of tangent line do we have at this maximum? Remember, r of t is a twice differentiable function. Okay, that was stated earlier. R prime of t is, where is it? Yeah, right here, twice differentiable. Okay, so that means that all critical points are going to be horizontal tangents. You don't have any cusp corners, vertical tangents, discontinuities is not applicable here. Okay, so we have a horizontal tangent. That's the type of critical point that we have, a horizontal tangent at t equals 45. Okay, so we have a horizontal tangent there. What does that tell us? It tells us that the derivative of this function is going to be equal to what? What kind of slope do you have when you have a horizontal tangent? You have a zero slope. So r prime of 45 is at its maximum, so the derivative at that point is basically the slope of the tangent line. But since it's a maximum, right, you have a maximum value. What is the slope of the tangent line there? That's basically the derivative at that point. So now let me fix my tangent line. So that basically is going to be 0. Okay, so the derivative of r prime of t, which is r double prime of t, r double prime of 45 is going to be equal to 0 at this extrema. Okay, so in order to get full credit, you have to do two things. First of all, you want to state that r double prime of 45 is equal to 0. That's the answer, because the question asked you for the value of r double prime of 45. Okay, and you get 1 point for stating this, and also you get another point for your explanation. Okay, stating that you have a critical point of horizontal tangent line and the existence of an extrema or maxima at that point. Hence, the derivative will be equal to 0, a horizontal tangent line. Okay, so you get a total of 2 points for question 3B of this exam. All right, let's take a look at question 3C. It says approximate the value of the integral from 0 to 90 of r of t dt using a left Riemann sum with 5 sub-intervals indicated by the data on the table. Is this numerical approximation less than the value of the exact area? Explain your reasoning. Okay, so let's start by taking a look at the formula. Okay. So we're going to be looking at the formula for the left rectangular approximation. So what is the left rectangular approximation? So what you want to do is you want to just, I'm just going to create an arbitrary interval. So we have, let me make it similar to this problem here. Okay, so for this problem we have 1, 2, 3, 4, 5. Okay, so we're gonna have 5 rectangles, 5 subintervals. So this is just a formula, okay? So we're gonna start from x1, okay? Because we have 1, 2, 3, 4, 5, 6. Okay, so we have x1. I'm just setting up the formula for you, okay? x2, x3, x4, x5, and x6, okay? So if you have these intervals, then you're gonna have 5 widths, okay? With 1, with 2, with 3, with 4, with 5. Now, if you're doing left rectangular approximation, right rectangle approximation, if you're doing the midpoint approximation, these widths are not going to change. You're independent of that, okay? What's going to change is the heights. Okay, so for left rectangular approximation, so what we're doing is basically we want to approximate the exact area from x1 to x6 of some function. All right, I want to approximate it using left rectangular approximation or the left Riemann sum. Using 1, 2, 3, 4, 5 subintervals. So what's going to happen is that we're going to be creating 5 rectangles, okay? But when we are determining the length of our rectangles, we're going to ignore the rightmost endpoints. Left means you're going to pick all the values to the left of the right endpoint. Okay, that's LRAM. If we're doing RRAM, we ignore the first one. And if we're doing midpoints, we just find the average value of these intervals, and then that's what we're going to use, the midpoint values. Okay, so let's see what I'm talking about. So we're going to do the height of the first rectangle, which is f of x1 times the width, w1, plus, I'm going to be running out of space, so let me make some room here. Okay, so that's going to be the area of the first rectangle, and then we have plus f of x2, that's the height of the second rectangle times the width, plus f of x3, that's the height of the third rectangle times the width, plus f of x4, that's the height of the fourth rectangle times the width, plus f of x5, that's the height of the fifth rectangle times the width. Okay, so for LRAM, notice we started with x1 and ended at x5. If we were doing the right rectangle approximation, we're going to start from x2 and end at x6. Okay, so this one will get ignored, but in this problem, we're ignoring the rightmost endpoint. Okay, another thing you want to note in our formula is note if f is increasing, LRAM is basically going to reside underneath the entire curve. So LRAM is going to be an underestimate. It's going to be under, all right? I'll show you what it looks like in a second. That's if f is increasing, like in this case right here. But if, I wrote it twice. If f is decreasing, if f is decreasing, guess what? If f is decreasing on that interval, then LRAM is going to be an overestimate. It's going to be bigger than the exact area. Remember, rectangular approximations are just used to estimate the area underneath the curve. The integral tells you the exact area, okay? Because in this question, we're asked if this approximation was less than the exact value or not. So we should know what the answer is just based on that. Now I'm going to apply the formula to this scenario we have right here. You don't need to use the graph, you can just use a number line. But I just want to give you a visual as to what the rectangles look like, okay? So in this problem, we're going to be using, this is our x1. 1, 2, 3, and then we have 50. 4, 5, and then guess what? The last one right here, 90, we're gonna skip that. Okay, since we're doing LRAM, we're just gonna pick all the points to the right of the left, to the left of the right endpoint. So this is what your rectangles are going to look like. So you have, let me make it the dotted line. Let's change the color to blue. Okay, so we have the first rectangle will be determined by x1, so that's the height right there all the way to the next interval. The next one right there, x2 determines the height of the second rectangle up to x3, which is 40, and that determines the height of the next rectangle all the way to x4. x4 determines the height of the fourth rectangle all the way to x5. And x5 determines the height of the fifth rectangle. Okay, we don't use x6 here because we're looking at the left rectangle approximation. So you notice the area underneath the curve, see this rectangle right here? You see how the area is missing the spaces right here. So that's why if a function is increasing, the LRAM is an underestimate because it's going to be leaving spaces underneath the curve, okay? But if it were decreasing, the exact opposite will happen. LRAM will actually lie above the curve. Okay, so this is what we're going to be computing the areas of. Okay, we're going to be accumulating the area of these rectangles. If you took elementary geometry, you know how to find your area, right? That's what we're doing. We're just adding up the areas of these rectangles right here. You don't even need to remember the formula. Just setting up the intervals correctly should help you with the whole process, okay? So one thing I really like to advise you to always do is draw a number line and set everything up clearly first so you don't get confused when you are plugging in the values into your formula, okay? So into your rectangle. So you have 0, we have 30, and then 40, and then 50, and then 70, and then 90. Okay, so we just need x1 to x5, and then we need 5 widths, okay? So this is x1, x2, x3, x4, x5. This doesn't really count, all right? It just helps us find the width. So, and then we need the widths. All right, so width 1 is 30. And then the second width, how wide is the second rectangle? W2 is 10 units wide. W3, the third rectangle is 10 units wide also, as you can see here, 10, 10. And then this one is 20 units wide. W4, 20. And then the last rectangle, how wide is it? 70 to 90. W5 is 20 units wide. Okay, so that's all we need. Let's rewrite the formula again just to refresh our memory. So the integral from 0 to 90 of the function r of t dt can be approximated with the left rectangle approximation, which is r of x1 times w1. Now let's pause for a second just to make sure you understand. What is this? This is the area of the first rectangle. This is the length times the width, okay? R of x2 times w2 plus r of x3 times w3 plus r of x4 times w4. That's the fourth rectangle plus r of x5 times w5. Okay, so let's plug in the values that we have. We're going to have r of 0, r of 0 times the first width, which is 30, plus r of 30 times the width, which is 10, plus r of x3 is 40, times 10, plus r of x4, which is 50, times w4, which is 20. It's good to label so you don't get confused and mix stuff up. And then r of 70, that's x5 times the width of the fifth rectangle, which is 20 units wide. Okay, and then evaluate the function at these values, just use your table to speed up the process. We have 20 times 30 plus 30 times 10 plus our 40 is just 40 times 10 plus r of 50 is 55 times 20, and then r of 70 is 65 times 20. And then if you calculate all of this and do your computations, you end up with 3,700. Okay? All right, and then we're asked, is it less than the actual value? The answer is yes. Okay? And then we can't just say yes, we have to explain our reasoning. So let's see how they structured it so we can write it properly. It says, is a numerical approximation. Yeah, so right. The numerical approximation is less than the exact value, because the function is increasing. Okay, the function is increasing on that interval, and LRAM is an underestimation whenever a function is strictly increasing. Okay, increasing on an interval. All right, so that's that. All right, let's take a look at question 3D. It says for 0 less than or equal to b less than or equal to 90 minutes, explain the meaning of the integral from 0 to b of r of t dt in terms of full consumption for the plane. And then explain the meaning of 1 over b times the integral from 0 to b of r of t dt in terms of full consumption for the plane. Indicates the unit of measures in both answers. Okay, so two formulas that we want to keep in mind for this problem. First one is the integral from a to b of some rate as a function of time dt. Now, what is rate times time? You want to remember quantity is equal to rate times time, or distance. Well, in this case, it's quantity of gasoline that's used, or amount. So what we're doing is we're accumulating quantity over a period of time. Okay, so over a period of time, this integral represents the total amount or total quantity of fuel that well, in just this formula. Okay, let's stick to the formula first and then we'll apply it to this scenario. This formula basically represents the total amount accumulated. The amount could be anything. It could be dollars, it could be water, whatever. Total amount accumulated from t equals a start time to t equals b. All right, so that's the first formula you want to keep in mind. The next one is the average value, not average rate of change. Two entirely different things, okay? The average value of a function, or average, is equal to 1 over b minus a over, 1 over b minus a times the integral from a to b of the function with respect to time. Okay, so that's the average value. Now, let us take a look at the first part of question 3D. What is the meaning of the integral from what is the meaning of integral from 0 to b of r of t dt? So the integral from 0 to b of r of t dt means the total amount of what in the context of this problem? Of fuel. Okay, total amount of fuel consumed from t equals 0 to t equals b minutes. Okay, or another way you can say it is total amount of fuel consumed in the first b minutes. Okay, from t equals 0 to t equals b minutes. This is what that integral expression represents, all right? Okay, and then the second part of the question, D, what is the meaning of 1 over b times the integral from 0 to b of r of t dt? Well, this is slightly tricky. If I write it like this, 1 over b minus 0 times the integral from 0 to b of r of t dt, you can see that this formula matches this second formula right here. B is B, A is 0. Okay? So this is basically equal to our average. And what is R? R is the rate of fuel consumption. Okay, so the average value of the rate of fuel consumption, this is what this expression right here means. Okay? Do not forget, we want to also include units of measure. So let's go ahead and write this down. So 1 over b minus a, 1 over b times the integral from 0 to b of r of t dt, let's see, means the average value of the function. What is the function here? Is the rate of fuel consumption. Okay, so the average value of the rate of fuel consumption using the name of the function, rate of fuel consumption, in, okay, what's the unit of measure here? What's the unit of measure? Now, let's do the calculation real quick. B minus, this is time, okay? So B minus 0, the independent variable in this problem is time. So we have 1 over time. And then rate times time is quantity, okay? So when we're talking about quantity here, we're talking about the quantity of gasoline or amount of gasoline, and that's in gallons. So this is 1 over time multiplied by gallons over 1, okay? All right, oh well, I put time. So time, what's the unit of time here? So this is volume, amount, and this is time. The unit of time in this problem is minutes. Okay, so we're looking at time and volume. If you multiply these together, you're looking at gallons per minute. That's the unit, okay? So this expression is the average value of the rate of fuel consumption in gallons per minute. In gallons per minute. From t equals 0 minutes to t equals b minutes, or you can say in the first b minutes of flight. Okay, so that's that. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming AP Calculus AB exam, do give us a thumbs up. Your positive feedback is very valuable to us. Don't forget to ask any questions or comments in the comment section below. We'll be more than glad to support you. And you can also subscribe to our channel for updates to other cool calculus tutorials such as this. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day. Goodbye.